so much.
Sure thing. All right. And yeah, just bring it by when you're ready.
I will. Thank you. Okay. Technology is an amazing thing, isn't it? All right, let's make sure we can get this. Now, at any point while I'm going over this, if you guys can't see what I'm doing on the screen here, raise your hand and say, hey, you're not showing us the right screen. This used to be able to zoom out of this, but I tried this today and it won't zoom out anymore. So I think that's the limits of our zooming out, but that's pretty good. I'll make it a little bit higher. Okay. All right. I think we'll go. Okay, so this front page kind of goes through what I'm going to tell you verbally right now, how we're going to go through some of these reactions. So if you don't get it or if you don't understand my explanation, make sure you read all this stuff. All right, so let's try with starting with the really simple number one, mole relationships. Now, this is the BCA diagram. BCA diagram. So when I say in lab, please use or create a BCA diagram, this is what I'm talking about. And it will help you so much in lab, in this class and in 152. And when you get to Chem 152, BCA changes to ICE, which is basically the same thing we're doing in here. You're going to get a preview, and when you get to Chem 152, fully 3 of the 8 chapters you cover in 152 use this ICE diagram thing, so you're going to be way ahead of your peers. Everybody else is going to be scratching their head, going crazy, and crying, and you're going to go, thank you, Dr. Wood. I'm going to send you good karma waves on the airwaves because you helped me understand BCA. All right, the first thing you need to know is when you fill out a BCA diagram, you got to do it in moles. So we have to know how many moles you have. So you have to take whatever masses or units they give you and convert it to moles. So that's why I showed you how to make that conversion using molar mass first. So first one says, hydrogen sulfide gas, which is this stuff right here, burns in air to produce sulfur dioxide and water. How many moles of oxygen gas would be needed? So we want to know how many moles of oxygen gas would be needed to completely burn 8 moles of hydrogen sulfide. So we got 8 moles of this to start with, of the hydrogen sulfide. Well, I think there's a reason that there's those little blanks in front of these substances in the equation. What do you suppose those little blanks are indicating to us? We need to balance it. So you guys balance it and see what you think the coefficients are. I'm going to take an eyeball look at it here. Oxygen, it looks like the one thing that's messed up because we got 2 here and we got 3 on the product side. So I'm going to throw a 2 here. See what that does. I think that means we're going to have a 2 here. Why don't you guys try and balance these and see what you come up with. So then 2 times 2 is 4. So if we put a 3, that would be 6. We could do 2 there. Does that do it?
Yeah.
2 times 2 is 4 hydrogen. 2 times 2 is 4 hydrogen. 3 times 2 is 6 oxygen. Let's save oxygen for last. 2 sulfur. 2 sulfur. 3 times 2 is 6. 2 times 2 is 4, 5, 6. All right, so I believe we're balanced at this point. All right. So if you look at this and you say you got 8 moles of this and it responds in a ratio of 2 to 3, you go, I'm not quite sure how that's going to work out. So if we have 8 moles of the H2S, I just do a simple mole-to-mole bridge ratio, and I say moles of H2S. And what do I want to figure out moles of? Oxygen. So I want to go moles of O2. Then I simply use the coefficients that are in front of the substances in my mole ratio, just like you've done before. So O2, coefficient is 3. H2S, the coefficient is 2. So now in your calculator, you're going to punch in 8 times, open parentheses, 3 divided by 2, enter, and what do you get? 12. All right, so 12 moles of O2 would be needed, right? Because if we use up all 8 moles of that, now here's how the BCA chart works. B is before, so I'm going to signify in my BCA chart how much I had to start with. I'm also going to signify that I used every smidgen up that I started with, and I'm going to end up with none of that left over. All right? Here, I just figured out over here that I'm going to need 12 moles of this stuff. So now I can punch that value in here, 12 moles of this stuff. I'm going to use up all 12 moles of it during my reaction. I'm going to have none of it left. Now we need to do the products, because that's just as important to look at the ratios in comparison of the products. Would it be easier to compare a 2 to 2 ratio or easier to compare a 3 to 2 ratio? I like 2 to 2, right? That's the same as 1 to 1. So if I'm using up 8 moles of this stuff and it's the same ratio as I generate this stuff, how much of this should I have generated? 8. So if it starts out at 0, because remember when you're doing a chemical reaction, you start with the reactants, and products, you start out with none of those things to start with, right? So if I use up 8 moles of this and it's a 2 to 2 ratio, I should generate 8 moles of this. So I'm going to have 8 moles at the end. So in the change column, you always want to signify, are you losing it or are you gaining it? Generally, reactants, you're going to lose it. Products, you're going to gain it. Once again, a 2 to 2 ratio is easiest to compare. So if I'm burning up 8 moles of this, and it's the same ratio as I generate of water, how much water should I generate? 8 moles. So plus 8 moles, and you're going to end up with 8 moles. All right. The first example is uber simple, because I want you to get used to filling these out in moles and thinking about reactants versus products. Reactants get used up, products are generated. So now they're going to get a little bit more complex as we go through. The next one, propane. Now they're going to ask you to write the equation. C3H8 is propane. That's the same stuff that's in your barbecue. We're going to say it's in gaseous form. Burns in air. So what do we have to have in order for combustion to occur in air? Oxygen gas, O2 gas. And I think this is probably complete combustion. So if it's complete combustion, what are our products going to be? Very good. CO2 gas, plus since it's combustion, it's probably going to be hot, so we'll say that the water is H2O. All right, now we got to balance this one. We've got 3 C's there, so I'm going to throw a 3 there and see what happens. 8 H's, throw 4 there and see what happens. Now I've got 3 times 2 is 6 oxygen here, plus 4 oxygen. I got 10. How can I make 10 over here? I want 10. Throw a 5 in front. All right, so now our equation is balanced, right? Can't reduce it any further. Follows the law of conservation of matter. Now it says if 12 moles of carbon dioxide are formed. So remember, we've got the BCA. Before you started, what changed? Add or subtract, and what do you have left over at the end of the reaction? Remember, products always start out as 0 in this class. We don't have any products that we're starting with. So we're going to start out with 0. It says if 12 moles of carbon dioxide are formed, so plus 12 moles, and that means we had 12 moles at the end. So we generated 12 moles. So now I want to go and I want to compare the ratios and proportions. If I used up, or if I generated 3 here, what would it be easier to compare? A 3 to 5 or a 3 to 1 ratio? 3 to 1. 3 to 1 I think would be easier. So am I going to need 3 times as much of the propane or 1/3 as much of the propane? 1/3, because I make 3 of those for every 1 of those I use up, right? So if I use up 12, if I generate 12 of these, how many of these am I going to have to start with in order to make 12 of those? 4, right? 4, 8, 12 is 1/3. And if you're not sure how to do that, and it's not in your brain, it's not an easy whole number like that, you simply do it, it's on the back side of this paper. Here we go. Oh, no, we'll do it on the corner here. We'll just say 12 moles of CO2. And we want to go from moles of CO2 to moles of the propane, C3H8, and it's a 1 to 3 ratio. So if you're not sure, you just set it up like this as a conversion going the mole-bridge ratio, right? That's your mole-bridge ratio conversion factor. 12 divided by 3 is 4 moles of C3H8 are necessary. So I go back to my BCA table, and I'm going to say I'm going to start with 4 moles of that. I'm going to use up all 4 moles of that. And I'm going to have none left. All right, now I've got a ratio between the propane and the oxygen. What's the ratio between the propane and the oxygen? 1 to 5. So if I use up 4 of those, how many of these am I going to need to have to get rid of all 4 of those propanes? 20. How'd you figure out 20? That's correct. It's 5 times as much, right? So I need to start out with 20 moles of this, which I'm going to burn up, and I have none left over. Let's fill out the last bit. What would be the easiest ratio in comparison to use with the water here? Which one? The propane, I would think, right? So if we're going to use up 4 of those, and it's a 1 to 4 ratio, how many of these am I going to generate? 16. All right. You guys are getting this. All right, how are we feeling so far? On a scale of 1 to 5, 1 meaning I have no idea what you're talking about, and I hate this. 5 is I could probably explain this to somebody else. All right. Let's skip up to, since you guys are feeling pretty confident, we'll just skip a couple pages and go to some of the harder ones now. Maybe we should get our brains oxygenated, right? Do you feel your head's expanding? Okay, smarty pants. I heard you, Cody. All right, let's try number 4. The poisonous gas phosgene. There's a funky looking stuff. COCl2, and it's a gas. Reacts with water, and what's the formula for water? H2O. Did you know that they were having those really cold temperatures in Minnesota in the Midwest? They said don't even go outside or talk or breathe for more than 5 minutes without going inside. You know why? Because the water in your mouth and in your lungs will freeze and it will hurt your lungs if you're outside more than 5 minutes. Isn't that crazy? The water in your lungs would freeze and crack your lungs tissue. That just, like, Arizona, you don't even think about that, right? That's crazy. It's crazy. All right. To form hydrochloric acid, what's the formula for hydrochloric acid? Those of you that just finished your nomenclature quiz? HCl. And we know that that's going to be, what's our symbol? AQ. Dang, my students, you guys are killing it. You're giving them the answers under the table, aren't you? Haley. And carbon dioxide, which is this stuff, right? CO2. I'm teasing you, Cody. All right, got to balance this thing. Why don't you guys try it, and I'll attempt it up here. Let's see here. Try that. Carbon. I think that's all we need. Is it balanced now? With just a little 2 there? Oh, that's pretty easy. All right. How many moles of hydrochloric acid would be formed? So we want to know how many moles would be formed from 0.835 moles of phosgene. So 0.835 moles. All right, well, we're going to burn up all that. So we're going to take all that away. We're going to have none left over, right? Now it's not nice whole number ratios. But if I burn up 0.835 of those, these are 1-to-1 ratio. How much water would I have to start with also? 0.835, right? I use up all that. I have none left over. Now my phosgene or phosgene, I don't know. Phosgene to hydrochloric acid ratio is what? 1 to 2. So if I use up 0.835 of that, how much of the HCl am I going to generate? 1 point, what's the number? 1.67. Alrighty, moles. If I start out with that, you guys are getting pretty good at this. How much CO2 am I going to be able to generate? 0.835. Oh, see, this isn't as hard as I said it was going to be, did I? I faked you out. It's not as hard as I said. All right. Well, if I said I want to know the mass, what mass of H2O could you produce? Where do we go from here now that we have our nice BCA chart in front of us? I'd need the molar mass of water, which it happens to be 18 grams per mole. What would I do with that information? Well, I would know that how much of the water did I make? 1.67 moles. Wouldn't that be a good number to start with? So I could say 1.67 moles of water. And what would I have to do to figure out the mass of water I produced?
Multiply it by grams over mole.
Grams over moles. See, you guys knew more about this than you thought you did, huh? And that would give us grams of water. If I wanted to figure out, well, this is not going to be a good problem for that one. We'll go on. All right, I'm going to let you do the rest of those on your own. Now we get to limiting reagent. Dun, dun, dun. Everybody's favorite kind of calculation. And I'm going to have you do it in a couple different ways. I'm going to have you do it not only with calculations, but I'm going to have you draw pictures. Remember, I told you next Monday when you come into class, your exam is due next Sunday night. You have to take it by next Sunday night. Next Monday when you come in, I'm going to give you a sheet that looks very much like this. I'm going to give you it's going to be a different equation, but it's going to have a box for before, a box for after, and it's going to ask you the same exact questions over a different equation. So if you know how to do this, this is going to be 25% of the points on your Unit 1 exam is being able to do this exact thing. All right, so if you're not getting it, make sure that you ask questions because this is the practice time for this particular thing. All right, the question starts. Write the balanced equation for the reaction between hydrogen and oxygen. All right, so hydrogen gas is what chemical formula? H2. So we're going to put a little G next to it. Oxygen gas is O2. And if we put those things together and spark a little spark and an explosion happens, what do you think is going to generate as a result? What do you know that's super common that you probably have had some of today that has hydrogen and oxygen in it? Good old H2O, right? H2O. The reverse of this process is the process that they could use to generate hydrogen gas. Remember I always like to get up on my sustainability soapbox. My sustainability soapbox is that we should be driving cars that are powered by hydrogen or electrical cars rather than combustion engines. And the reverse of this process, if you go in that direction, you can take water, run an electrical current through it, and it will separate it into hydrogen and oxygen gas. We could take the oxygen gas, give it to patients in homes that need oxygen to breathe, and then we could power our cars with hydrogen gas. We just need to develop a hydrogen economy. Unfortunately, we're going in this direction, in this reaction, not in the reverse direction. So this is one where energy comes back. All you have to do is light a little spark, and you get water. That's not balanced, however. What would I do to balance this equation? 2 in front of the H2O? I think in front of the H2. I think you're right about that. So 2 times, and I think we need a 2 here too. I think that fixes things. All right. So there's our balanced equation. Now it says, suppose that 4 molecules of hydrogen gas and 4 molecules of oxygen gas react to form water. So I'm going to draw them. Here's my hydrogen. It's little. Oxygen is going to be big. And we'll actually make hydrogen gas, since it's diatomic, be 2. All right, so there's my hydrogen gas. And there's my oxygen gas. There's my legend. So it says, suppose that 4 molecules of hydrogen gas. So I got 4 of those. So please draw them in. 1, 2, draw them in randomly, like gas molecules would be, right? They're randomly contained in the box, and they have all kinds of motion. They're moving all over the place. So I got 4 of those. And 4 molecules of oxygen gas. So draw in the 4 molecules of oxygen gas. 1, 2, 3, 4. All right, so I got 8 molecules of gas in my container. Now I want to make water. So this is the before. These are the reactants. And the after is the products. So now I'm going to go through. I'm going to see water is going to look like this. It's got an O, and it's got 2 H's. Water actually looks a little bit like Mickey Mouse, right? It's got those non-bonded electron pairs over here pushing the hydrogens on one side, if you remember your molecular geometry. So now I'm going to make as many waters as I can. So I got to use 1 hydrogen, another hydrogen, and an oxygen, and I'm going to move them over into my product box. So now I've made 1 water. See, I crossed out 2 hydrogen atoms, 1 oxygen atom, and I moved them over here to my product box. Going to do the same thing. 2 more hydrogen atoms, another oxygen atom. I make another water molecule. Okay. 2 more hydrogen atoms. I'm crossing out 1 oxygen. Make a 3rd water molecule. Last one, I'm going to cross out those 2 hydrogens, 1 more oxygen, make a 4th water molecule. All right, and I also have some things left over. What didn't I use up that were left over? 4 oxygen atoms, or in fact 2 molecules of oxygen are left over, right? All right, so that's the before, and that's the after. Now the question says, how many molecules of water can be produced? Well, how many did I make? 4. Which reactant is in excess? Meaning, which one do I have stuff left over? Oxygen, O2, gas. How many molecules of excess reagent are there? 2. All right, so now we're going to do the BCA. We're going to put 2 H2s plus O2 yields 2 H2Os. Now the before, remember in the problem it said I had 4 molecules. You can say that's the same as 4 moles. A molecule and a mole can be called the same thing as long as they're 4 units of that thing. So I got 4 moles of this, or 4 molecules. I also got 4 moles of this, or 4 molecules to start with. And I have none of the water to start with. 0. All right? Now, because it's a 2-to-1 ratio, which one of these is going to get used up first? Since it's a 2-to-1 ratio. The hydrogen's going to get used up first, and all of it's going to go bye-bye, right? Minus 4 moles. I'm going to have none of that left over. You see how that worked? I see some confusion back there, ladies. Do you have a question for me? I saw your brow got furrowed. And you asked her.
I was having trouble seeing it.
Okay, feel free to move on.
Can we make it full screen?
Ooh, thank you for that suggestion, Becca. Does that help? Hello? Please make sure to ask me these things. I'm not super techno-savvy. We got full screen. Does that make it easier to see now in the back?
Yeah.
Hot diggity dog. All right. Make sure we do that from now on. All right, so we used up all that. If I'm starting with 4 of that, and it's a 2-to-1 ratio, how many of those 4 am I going to use up? 2, right? So minus 2 moles. And I'm going to have 2 moles left over. All right. Now, here's the key. Am I going to compare a 2-to-2 ratio or a 1-to-2 ratio? What would be better? 2-to-2 or 1-to-2? I like 2-to-2, right? If we used up 4 of this, how many of this should we generate? 4. So plus 4 moles. I'm going to have 4 moles at the end. So it's the same answers, right? 4, O2, and 2. All right. So that's BCA. That's the molecular, microscopic perspective. That's the symbolic perspective. And then we've got the mathematical perspective too. So you're thinking in 3 different ways here. All right, let's do some of these. When sodium hydroxide reacts with sulfuric acid, we're doing number 4 here. Water and sodium sulfate are the products. Calculate the mass of sodium sulfate produced when 15.5 grams of sodium hydroxide are reacted with that much sulfuric acid. Holy smokes. All right, before we can do anything, where do we got to start on this beast? Balanced equation. So when sodium hydroxide, what's the formula for sodium hydroxide? NaOH. So let's do NaOH. All right. I would say, what do you suppose that's going to be? Solid, liquid, gas, aqueous solution? Your experience, what do you think? Probably an aqueous solution. Based on your experience, it's a base, which is generally an aqueous solution. Sulfuric acid, they told you the formula. Also an aqueous solution. So since you've got a base and an acid, what kind of a reaction is this? Neutralization. So what are the products of a neutralization reaction? Always. Water and a salt. And what's my salt going to be? It's not going to be just NaCl. What kind of salt is it? Na and the SO4. All right. So here, Na is +1, SO4 is -2. What's correct nomenclature for sodium sulfate if Na is +1 and sulfate's -2? Na2SO4. You suppose that's going to be solid, liquid, gas, or aqueous solution? generally salts that are produced in acid-base reactions are going to be aqueous solution. I don't think that's balanced, so let's balance it. I think we probably need that there. 1 SO4. We got 4 hydrogens, only 2 there, so probably 2. 2. I think we're good. Is that balanced? I think we're pretty good. Anybody see anything glaring error in my balancing of this? If you can't balance the equation, generally the problem is that you haven't created correct nomenclature for products. So if you're having a hard time balancing equations, check the products. All right, so now it says calculate the mass of sodium sulfate produced. Okay, so we want to know how many grams. I like to draw pictures when I'm doing these kind of calculations to keep myself on track. How many grams of that junk is produced when 15.5 grams of this, so we're starting with 15.5 grams of that, are reacted with 46.7 grams of the sulfuric acid? Well, we can't fill it out in grams. So what do we have to do to get it into a form that we can use to fill out the BCA table? Got to change it to moles. So I'm going to take my 15.5 grams of the NaOH, and I want to go from grams of NaOH to what? Moles of NaOH. And 1 mole, let's see, sodium, I think it's 40 grams per mole because I've done so many of these calculations to actually create aqueous solutions of sodium hydroxide. I actually have that number memorized. So if I'm wrong, let me know, but I'm pretty sure it's 40 grams per mole. Okay? So what's 15.5 divided by 40? What's the number? Somebody with a calculator handy. Some number less than 1.
0.387.
Sounds good. Moles of NaOH. All right, so now I can start my BCA diagram. And you may want to do some of these calculations on a separate piece of paper because it gets a little bit crowded. All right, so we start with 15.5 grams, which is 0.387 moles. So that's my B, 387 moles. You got to fill out the BCA chart in moles. Same thing with the H2SO4. I'm going to do it down here. 46.7 grams of H2SO4. I got to go from grams of H2SO4 to moles of H2SO4. Oh, let's see. Sulfur. Who's got a periodic table? How much does sulfur weigh?
32.065.
Thank you. And oxygen is 16 each times 4 is 64. And then hydrogen is 2 more. All right. So if we add all this up, say 98.1. All right, so what's 46.7 divided by 98.1? It's about 0.5 something, isn't it? Maybe 0.4? Somebody with a calculator. What's 46.7 divided by 98.1? What do you get?
0.476.
Perfect. Moles of H2SO4. So now we're going to put that number here. So we got 0.476. So 0.476 moles. All right. You can't fill these things out in grams because, as you can see, the molar masses are real different. If you just looked at the grams, you said, well, we got a whole lot more of the H2SO4, and it's a 2-to-1 ratio, so I'll bet the NaOH is going to run out first. Well, that's not necessarily true because molar masses are different. So now you can't really tell, well, I can kind of tell by eyeballing it, which thing you're going to think is going to run out first. I would say, looking at this, the NaOH is going to run out first. How did I know that?
Small.
It's a smaller number, first of all. And that was if it would be a 1-to-1 ratio, but it's not even 1-to-1. What's the ratio between NaOH and sulfuric? It's 2-to-1, so we use up that stuff twice as fast, right, as this. We use twice as much of this as we do of this. So since there's already a number that's lower than it's starting out, it's all going to get used up, right? If you're not sure how to figure that out, you just say 0.387 moles of NaOH, and you go moles of NaOH to moles of sulfuric, and you put in the 2-to-1 ratio, .387 divided by 2 is going to be 0.163 approximately. So I would need 0.163 moles of the sulfuric. I got way more than 0.163, right? Way more than 0.163. So I know that this is going to be my limiting reagent. I always like to put that on there so I know what the limiting reagent is. So I'm going to use all that up, minus 0.387 moles. I'm going to have none left over. Now it starts to get a little more complicated. I'm going to use all that up, but am I going to use all of this up?
No.
No. How much of that will I use up? How can I figure that out? This is the hard part. Here's now it's getting harder. How can I figure out how much of that 0.476 that I'm going to use up? Wouldn't it relate to how much of this I used up?
You just subtracted the 3.87.
Well, but am I going to use 0.387 of this up? Because it's a 2-to-1 ratio. How much of that am I going to use up?
You subtract 0.136 by 0.476.
I'm going to use up 0.163, aren't I? Aren't I going to use up 0.163 or half? What's half of this stuff? What's half of this? 0.163, right? Minus 0.163, right? That's how much I'm going to use up. Did you see where I got that? So if I use up that much of this stuff and it's a 2-to-1 ratio, I'm going to use half as much of that as I did of that, right? If I use 0.387 of that, 2-to-1 ratio, I'm going to use half as much here. So that's where that number comes from. So what's 0.476 minus 0.163? What is it?
313 moles.
Thank you, 313 moles. All right. I'm starting out with 0 of these. Now, which one of these? I can't, this is a limiting reagent problem. I can't just use the thing that's easy. What do I have to use in order to determine how much of the product was formed? Should I use the B line or should I use the C line? Think about that. Am I going to use the before or am I going to use the change to figure out how much of this I made? Yes?
Wait, so half of 0.387 isn't 0.163.
What is it? I didn't do the
It's
calculation.
like 0.19 something.
Is it?
Yeah.
Holy capoly. Oh, that's right, because I put 3.8. No?
So
387 divided by 2, somebody told me that was 0.163.
0.193.
Okay, well somebody must have gave me the wrong number over here.
I was going back comparing answers because I'm ahead, and I was like, you're freaking out.
Is it 9.3?
Yeah, I made a mistake on that.
Okay, that's all right, that's all right. I do those boo-boos all the time.
0.193.
Okay, so then we don't have 0.313 left over. How much do we got left over?
I have 0.28.
0.28.
I only rounded to 2 decimal points.
That's okay, that's all right, that's all right. Oh, and by the way, down here, you know, I gave you the answers so you can see if you're right when you're doing these calculations. That's pretty handy. So you can double check and see that you're doing these right, which is really the goal of this. Right? The goal is not to do the homework. The goal is to make sure that you know how to do the homework. All right. So now would I use the B line or should I use the C line to figure out how much of these things am I going to make? The C line, right? Because the C line is what was used up of the reactants. The B line is just what was there available. Okay. Before and change versus after. Before is like you open the fridge, right? What's in the fridge? What do I have available? You take out the junk that you need, right? Some of it you might use all of it. Some of you might only use a little bit of it. But then that's what you use. And then the after is what's left over in the fridge when you took the stuff out that you needed to make your recipe. All right, so over here, so we're going to use the C line. So should I compare a 2-to-2 ratio? Or should I compare 1-to-2 to figure out water?
2.
Well, I like 2-to-2. Well, if I burned up 0.387 of that, how much of the water should I have made?
0.387.
See how handy that is? This is like an accountant's way of doing stoichiometry. So we're melding, we got a hybrid, we got chem accountants here. All right, the Na2SO4, what should I compare that one to?
H2SO4.
The H2SO4, should I compare the B line or the C line?
C line.
C line, so if I burned up 0.193 moles of this, how much of the Na2SO4 should I have made? I'm going to generate 0.193 moles. So at the end, I would have 0.387 moles of that. I would have 0.193 moles of that. And now, the question asks how many grams. So I would take the 0.193, and I'm messing up my worksheet all over the place here. 0.193 moles of Na2SO4. Could I figure out how many grams that is? I surely could. I'd go moles of Na2SO4 to, what's on the top? Grams of Na2SO4. One goes in front of moles when you're going moles to anything else. Sodium, odd, weird fact, I know, is 23 grams per mole, and there's 2 of them. Isn't sodium 23? Am I right? I think I am.
Yeah.
Okay. Sulfur, I don't know what sulfur is offhand. What's sulfur?
32.
32. And oxygen is 16 each times 4 is 64. So that's 140 what?
142.
Thank you, hon. 142. So 142 grams per mole. Hopefully that times that gives me 27.5 grams. It's always reassuring when the answer comes out correct. It does? Yay! So you can see how BCA would be super helpful. How about another question? How about if I said, tell me the mass of excess reagent that remains? What is the mass of excess reagent that remains? Well, first of all, what is the excess reagent? What's left over? The sulfuric acid, right? Could you tell me the mass of that, knowing the moles? Yeah, it'd be pretty easy to figure that out, wouldn't it? Here's the beauty of the BCA. You don't have to do a separate calculation for every question. Once you fill out the BCA and you understand what it means, you just pull the numbers that you need and respond to the questions. Now, let me give you some strategy. BCA is most helpful when the questions are limiting reagent in nature. It's easier to use straight stoichiometry or the stoichiometry flowchart when there's no limiting reagent. It's much more efficient. So if you can use both methods, if you can use straight stoichiometry using the stoichiometry flowchart, apply straight stoichiometry to reactions that are not limiting reagent, and then when you get to these limiting reagent problems where they ask you all kind of difficult stuff, make sure you can do BCA. These are going to be very helpful in the lab because I'm going to say in lab things like, all right, I want you to figure out how much of these things you have to add together to create exactly 1 gram of this stuff. And I'll say, I want you to make 1 gram of that stuff. Now you got to figure out how many grams of each of these things to put together in order to make 1 gram of that stuff. So that's how these are going to be super duper helpful. And my suggestion to you is to practice all of these. Now, Billy, when you did this, did you use straight stoichiometry or did you use the BCA thing? Because you said you finished this whole worksheet, right? Or almost all of it?
I did just like straight stoichiometry, but then I kind of like wrote it how you had it because that's what you wanted.
Right, right. Do you understand what I'm showing you now based on the fact that you solved these problems with straight stoichiometry? Does this make sense to you? Because it's really the same calculation that you do with straight stoichiometry. It really and truly is. It's just a different way of accounting for the different parts of the reaction. And I promise, if you can learn how to do
It's
this.
just easier to keep track of everything. Like you lose stuff when you do like straight stoichiometry because you have like a whole lot of work in one spot.
Right, and you go, oh my gosh, now what did I just calculate? Was that how much was formed, how much I used up, how much was left over, whatever. And if you've got the BCA, it's all right there. So I know this may be foreign, and a lot of people don't like this when they first see it, but I can promise you that you'll thank me next year when you're in 151 and you go, she was right. That crazy chemistry teacher, she was right. All right, here's another one. Same kind of thing. Here's all the answers down here. So now some of these are limiting reagent. Some of these would be helpful to use BCA. So let's look at them. Must decompose. Okay, so I'm going to put LR next to limiting reagent problems. All right, number 1 is not limiting reagent. Number 2 is not. 3 is not. 4 is not. This one is going to be limiting reagent. is going to be limiting reagent. Limiting reagent, so we'll put LR, LR, LR.
So you only do the one with the.
No, you should do all of them. I'm just giving you the strategy to approach each of these with to be most efficient in your problem-solving methodology. Because when you get to the exam, and you're doing these problems on the exam, knowing the most efficient method is going to be super helpful. And the last one, yep, that one is definitely limiting reagent. So you need to do all of them, but these are non-limiting reagent, and these are all limiting reagent. These also get into this idea of percent yield. So let's do a problem with the last 15 minutes that we got that has to deal with percent yield, which is one of these other worksheets. So I'm picking and choosing a few of the problems on all these worksheets just to give you a sampling so that you can get a good start on these and finish the rest of them on your own. I also have a whole bunch of more packets that if you want another one so that you can do one, rough and then do one nicely to turn it in if you want to, that works as well too. All right, so percent yield. Now percent yield is something that we use frequently in the lab. And percent yield is different than percent error. Percent yield compares how much you should have made with how much you actually did make. So percent yield is the experimental yield. Experimental, make sure I spelled that right. Yield. Oh, can't see that, can you? That would help. Experimental yield divided by the theoretical yield times 100. All right. Theoretical yield is using stoichiometry in a perfect world. In a perfect world, you got two reactants, you put them together in a container. Every single reactant molecule that can find every other single reactant molecule will do so and find each other in that beaker and react. Is that reasonable to expect in a normal chemical reaction that every single piece of stuff that you have is going to find each other in the beaker and react? Probably not reasonable, okay? So that's why that's the theoretical yield. In a perfect world, that's what would happen. The experimental yield, where do you suppose that number comes from? The experiment. All right, so let's try that. It says, recall that liquid sodium reacts with chlorine gas. So what's the symbol for sodium? Na. Here's a good way I remember that. If you are on a low sodium diet, you can't have table salt, which is sodium chloride, NaCl, right? So my mom has high blood pressure, so I always tell her, you say nah for the sodium chloride, right? No, thank you. I know it's bad. All right, liquid with chlorine gas. What's the formula for sodium, or for chlorine gas? Cl2. It's one of those diatomics, right? Those 7 diatomics. When you see them as gases, they're always diatomic. Produces sodium chloride. What's this formula for sodium chloride? Good old table salt. Is it going to be solid, liquid, gas, or aqueous solution? Probably solid, I would bet. Probably solid. All right, is that balanced? Don't think so. I think we need a 2 there and a 2 there, and I think we're good to go. All right, you want to produce 581 grams of sodium chloride. So you want 581 grams. How many grams of sodium are needed? How is this percent yield? That's not really a good percent yield. Let's skip down. I'll let you guys finish that one on your own.
Maybe
3. Let's see. Ah, perfect one. We'll do number 3. Suppose 4.61 grams of zinc. What's the formula for zinc? Good old Zn. If it's a metal, is it going to be solid, liquid, gas, or aqueous solution? Solid. It reacts with hydrochloric acid. What's the formula for hydrochloric acid?
HCl.
Good old HCl. Is it going to be solid, liquid, gas, or aqueous solution? AQ. Yields zinc chloride. Here's a tough one. What's the formula for zinc chloride? Well, it's got zinc and chlorine in it, but what's the ratio of zinc and chlorine to each other? Cl2. Good. That's probably going to be an aqueous solution. And what else? Hydrogen gas. What's the formula for hydrogen gas? Good old H2 as a gas. All right. I think we got to balance that, so we'll put a 2 there. I think that fixes everything. All right, so we got 4.61 grams of this, 4.61 grams of the zinc with hydrochloric acid. Well, it's not limiting reagent, but that's okay. That makes our lives easier, right? You can use straight stoichiometry with this. How do I know this is not limiting reagent?
You just have excess of the hydrochloric.
Right. It says you've got allowed to react with hydrochloric to zinc chloride. How much zinc chloride you get? It doesn't give you a quantity of it. So you're saying you have to assume that it is excess. So that means you have lots, right, of that stuff. So we can use straight stoichiometry on this. So we're going to start with 4.61 grams of HCl, right? All right, now if we're using our stoichiometry flowchart, it's going to be a 3-step conversion. We'll go from grams of HCl to moles of HCl, moles of HCl to moles of, what's the next thing we're going to?
Zinc chloride.
Zinc chloride. Once we got moles of zinc chloride, then we're going to go to grams of zinc chloride. So that's the progression in the stoichiometry flowchart. Let's look at that real quick. Keep it up here on the overhead. Grams or number of particles, you got to go to moles of A to moles of B, and back to grams or to number of particles. In this problem, we're starting here at grams. We want to end at grams of the other thing. So we got to go 1 step, 2 steps, 3 steps in the problem. So that's what I'm going to do here. The first step, I'm going to take grams of HCl, I'm going to put it on the bottom. Grams of HCl goes on the bottom. Okay, that's my first step in the stoichiometry flowchart, grams to moles. So since I put grams of HCl on the bottom and I'm going to moles, I'm going to put moles of HCl on the top. Yes?
Why do you have HCl instead of zinc?
Thank you. I was not paying attention, was I?
I'm so confused on why.
Yeah, thank you. And please stop me when I mess up like that. Usually I give students a pencil as a reward, but I only have 1 pencil today. I owe you a pencil, Cody.
I'll hold you against that.
All right, thank you. All right, yes, it is important to have the right substance. No wonder some of you were looking a little confused. What the heck is she talking about? All right, so zinc and zinc. All right, so we're still doing the same spot, grams to moles. So we're going from grams of zinc to moles of zinc, grams of zinc to moles of zinc. 1 goes in front of moles when you go from moles to anything else. And looking on the periodic table, what's the molar mass of zinc? 65.4?
Yeah.
All right. So now I've gone from grams to moles. I have 2 more steps. So I'm just going to set up my other 2 conversion factors because I got to have 1, 2, 3 steps. Now grams of zinc is canceled, right? Now I'm going to take moles of zinc. I'm going to put it on the bottom of my second conversion factor. And now in my stoichiometry flowchart, I'm here at moles of zinc. I want to go to moles of what's the other thing that I want to go to moles of in the problem? Moles of zinc to moles of zinc chloride. Very good. Moles of zinc chloride. Now, where do the numbers come from for the coefficients in your mole bridge ratio? Where do those numbers come from? Balanced equation. So zinc chloride has a 1 coefficient. Zinc also has a 1 coefficient. All right. So now I'm going to take moles of zinc. I'm going to put it on the bottom here. Moles of zinc chloride, excuse me. And what's going to be on the top, because here I am in my flowchart and I want to go to grams. So what are the units in substance I'm going to put on the top of the last conversion factor? Grams of zinc chloride. All right. So let's see. Chlorine is 35.5 each, so that's 71 grams for zinc. Or excuse me, for chlorine. What's zinc's molar mass? 65.4? All right. So 136.4 grams per mole. So now in your calculator, 4.61 divided by 65.4, enter. we can skip this one because it's just times 1, right? Times 136.4, what number do we come up with?
9.615.
We'll just use 9.62 grams of zinc chloride. All right, but we still haven't finished the problem. They want to know percent yield. So what's this? Is this my actual or is that my experimental yield? That's my theoretical, excuse me. I should have said experimental or theoretical. This is the theoretical yield, right? That's based on stoichiometry and a perfect world. What's my actual yield here?
8.563.
Right, there's my actual or experimental yield. So it's a simple calculation, 8.56 grams divided by 9.62 grams times 100. And the answer for number 3 should be, on the answer sheet it says, well, we got the grams right, 9.61 grams of zinc, and that should be 89.1% yield. Hot dog, there it is. What a master planner I am on the timing angle here. Exactly enough time. If you'd like, I will post on the Canvas section the lectures that I did for my Chem 130 that deal with just straight stoichiometry. If you need a review, how many people feel like they need a review on just straight stoichiometry? Okay, I'll post those on Canvas. The 130 lectures that are just on stoichiometry, and then I'll post this one that is on stoichiometry and BCA and percent yields. All right? That's it for tonight, boys and girls. Thanks for playing along.